For over a century, neuroscience operated under a foundational assumption. The brain is an isolated, immune-privileged fortress. This historical framing evolved directly into our modern parenchymal models of Alzheimer's disease. We analyze the neural architecture and the resident immune cells, the microglia, as a strictly local, self-contained system. In this closed view, microglial failure is a local chemical problem. Resident microglia succumb to intrinsic oxidative craft and localized lipid burden, eventually losing their essential TGF-beta homeostatic signature and collapsing. Treating microglial biology as a standalone branch of neuroscience is operationally convenient. You can study the brain in a vacuum, but etiologically it falls short. The brain does not exist in a vacuum. A model that looks only at the local tissue structurally ignores the vast systemic circulatory and immune environment surrounding it. Consider the cognitive resilience paradox. Autopsy reports routinely reveal patients with severe amyloid and tau burdens who, in life, maintained perfect microglial homeostasis and sharp cognitive function. If microglial collapse is dictated purely by local oxidative load and lipid handling, these patients should have severe dementia. The local variables alone cannot account for this massive inter-individual variance. The missing variable sits outside the skull. Schwartz's protective autoimmunity framework introduces the systemic immune compartment into the equation. Microglial homeostasis is a two-compartment dependency, parenchymal tissue on one side and systemic peripheral immunity on the other. Alzheimer's occurs when both fail jointly. The local TGF-beta niche collapse is tied to peripheral T-cell exhaustion. We must track signaling bridges crossing into the brain. The choroid plexus serves as the critical bridge between these compartments, functioning as a dynamic immune interface rather than a passive barrier. Circulating peripheral T-cells actively govern this gateway by secreting interferon-γ. This interferon signal holds the gate open, licensing the controlled recruitment of bone marrow-derived monocytes into the cerebrospinal fluid. Once inside, these recruited macrophages engage amyloid and cellular debris using different machinery than the brain's resident cells. They rely on specific scavenger receptors, completely bypassing the metabolic bottleneck of the TREM2 receptor. These peripheral recruits execute a distinct transcriptional program. They initiate a prompt resolving response, clearing debris efficiently and transitioning quickly to tissue repair. Resident macroglia, by contrast, are prone to chronic destructive inflammation when overtaxed. By outsourcing the heaviest clearance tasks to these recruited peripheral cells, the brain reduces the metabolic and oxidative burden placed on its resident macroglia. The resident neural infrastructure maintains its protective TGF-beta signature specifically because it is receiving constant, highly capable systemic backup. The sequence of pathogenesis begins when that systemic backup fails. The first upstream driver of collapse is the age-dependent exhaustion of the peripheral T-cell compartment. Driven by the cumulative history of peripheral immune challenges, T-cells upregulate PD-1 and PD-L1 checkpoints. As they exhaust, systemic interferon-γ tone plummets. Without that interferon-γ signal, the choroid plexus gateway clamps shut. The recruitment of bone marrow-derived monocytes ceases immediately. The brain's peripheral salvage arm is cut off. The entirety of the pathological burden, decades of amyloid accumulation and cellular debris, is instantly shifted onto the yolk sac-derived resident microglia. Forced to process this massive load through the TREM2 metabolic pathway without any systemic assistance, the resident microglia exhaust their metabolic fitness, succumb to local oxidative stress, and lose their homeostatic signature. The collapse of parenchymal microglia is a direct response to systemic abandonment. Systemic failure eventually transitions from passive abandonment to an active assault on the neural circuitry. This phase is governed by the CD38 immunometabolic checkpoint. In the aged and diseased state, CD38 upregulation rapidly consumes NAD+. This depletes the cellular energy pools required to maintain a balanced peripheral immune profile. This metabolic stress triggers a massive spike in meningeal Th17 cells, flooding the environment with the cytokine interleukin-17. That systemic interleukin-17 signal penetrates the brain parenchyma. It commands the resident microglia along the borders to abandon homeostasis and execute an aggressive attack program. The microglia respond by releasing a specific enzymatic arsenal. matrix metalloproteinases 2 and 9, alongside ADAM-TMTS4. These enzymes have a highly specific target. They execute the rapid digestion of aggrecan and tenascin R, destroying the perineuronal nets surrounding parvalbumin-positive interneurons. A dysregulated peripheral signal actively orders the destruction of these cognitive networks, creating a physical bridge between immune exhaustion in the blood and cortical dementia. This dynamic addresses a major tension in the literature. McCall-Schwartz's models argue that adaptive immunity protects the brain. Other prominent researchers, like Donald Weaver, observe adaptive immunity driving pathology. This chart plots adaptive immune utility against disease progression, resolving the tension. In the pre-collapse phase, peripheral immunity is highly protective. Once the gateway closes, trapped immunity triggers destructive pathways. The inflection point is homeostatic collapse. Adaptive immunity's function is dictated entirely by the chronological integrity of the brain's systemic licensing. Therapeutically, this demands a compound approach. Interventions must operate simultaneously on the parenchymal microglial niche and the peripheral immunometabolic gate. Interventions targeting just one compartment face a hard ceiling. For example, applying local TREM2 agonists to resident microglia will stall if the peripheral NAD+ pools are still depleted. The underlying metabolic constraint hasn't been solved. In late-stage post-collapse patients, the required intervention is halting the pathogenic destruction. This means applying interleukin-17 blockers at the meningeal barrier to preserve the perineuronal nets. In early-stage patients, the goal is sustaining the protective phase. Administering PD-L1 inhibitors to circulating T-cells rejuvenates systemic interferon-γ tone and reopens the choroid plexus gateway. CD38 blockade addresses both compartments by restoring NAD+ metabolism, reviving exhausted T-cells while neutralizing the toxic Th17 response at the meninges. Halting clinical progression requires a coordinated molecular strike, rescuing the metabolic fitness of the systemic supply line while explicitly disarming the enzymatic attacks inside the cortex. Measuring single parenchymal variables, like top-line amyloid clearance, is an insufficient metric for clinical success under a dual-compartment reality. The necessary biomarker is a compound one, measuring systemic interferon-γ tone in the blood to confirm gateway patency, coupled with structural imaging of perineuronal bit integrity to confirm parenchymal survival. The historical doctrine of the brain as an isolated, self-governing fortress is conceptually incomplete. The nervous system is a localized ecosystem that requires continuous, actively gated licensing from the body's broader immune network. Ultimately, Alzheimer's disease represents the systemic expiration of the immunological licensing required to sustain the human brain.